Good morning. Welcome to Physics Studio. Hope you're all doing well. What I'd like to do today first is look at a couple of interesting examples relating to the third and the second right-hand rule. And then after that, we're gonna look at the way we've built a bridge between electrical energy and kinetic energy using the magnetic field. And that's the topic for today. So let's take a look at let's get to work and take a look at a couple examples. Now, besides being interesting, we also want to concentrate a little bit on how we represent these kinds of situations, right? And what we're looking for in your sketches, and a lot of you were getting this pretty well yesterday, is clarity and unambiguousness, right? All the features of the drawing, the magnetic field, the movement of the charge, the current, should be clear which arrows indicate them and what their direction is. So, first example, and you will find this in your reading for today. Something like this. Let's say, and we're thinking of right-hand rule number 3 right now. Let's say that we had a loop of wire. Right, and we're going to run a current through it, say positive to negative, such that the current is going to go like this, then it's going to go up here, going to be going that way, then the current's going down there. And let's say that we impose an external magnetic field. Say we have a huge bar magnet, and we've got the south pole of that magnet here. The north pole would be over here. Say we've got another huge bar magnet, and we place the north pole there. The south pole would be over here somewhere. Of course, you can't have a single pole. Now, if we do that, we're going to get a magnetic field relatively uniform between that goes from north to south. Right, that's our externally imposed magnetic field, which is what we need for right-hand rule number 3. Now, if we just think of just a simple test magnet, if we have a magnetic field going, say, in this direction, because we've got a north pole here and a south pole over here, and we place a test magnet in it, right, which means a compass needle, say like this, and we'll say that this is the north end of the compass needle, right? The red end, the north pole, and this is south. We know that this end is going to be strongly repelled by this north pole here and attracted by the south pole. So the north pole of the test magnet is going to experience force that way. This south pole here, on the other hand, will be repelled by the south and pulled to the north so that it will experience a force like that. And you can see if we have that center pinned into place, what it's going to do. It's going to immediately flip like that. And so whenever we have dealing with magnetic fields, we often get that twisting phenomenon. And then eventually it's going to twist so that if you had it lined up like this, with this being our north pole, and it's free to rotate, this is going to be pulled that way, and this will be pulled that way, and there will be no net force on it, so it will just sit there. Once it's at an angle of 0 to the magnetic field, it experiences no further unbalanced force. Now, down here, something a little bit similar is going to happen. Now, if we're running current through the wire, call this point A, call this point B, right? At point A, the current is going in that direction. And so if we apply our third right-hand rule to find the force acting on it, fingers in the direction of the field, thumb in the direction of the current, we'll find that this is experiencing a force that comes out of the palm. In other words, out of the page towards you. In other words, this side of this is being pulled toward you. So this is imperfect, we'll indicate that force like this. Now, if we go over to B, the current has gone around like this, down like that. The current is now going down. Right, this is our field B. And if we extend our fingers in the direction of the field, thumb in the direction of the current, the force comes out of our palm, and the force at point B is going into the page. And we'll imperfectly represent that like that. So this end here is being pulled toward you, and this end is being pushed toward you. If this is free to rotate, it's going to spin like that. Then once it gets to here, it'll start wobbling like that. But that's the first way you can produce mechanical motion out of an electrical field. Now, let's look at another example. Let's say that we have a field B, and let's just arbitrarily say the field is going into the board. Right, and that's our field B going into the board like that. And let's say that we have a positively charged particle. And we send that with some velocity v into the field. Right, as long as that thing's going along here, it's producing a magnetic field, but it's not experiencing any external field, so it's just going to go straight. As soon as it hits this field, though, it's going to start to experience a force that we define by the third right-hand rule. So, putting our fingers in the direction of the field and our thumb in the direction of the motion, the force comes out of the palm, and we find that when this positively charged particle gets to here, right, it's got a velocity in this direction, it's going to experience a force in this direction, and we know that if you have a force perpendicular to the velocity, what it's going to do, right? That thing's going to trace a circular path like that. Until it gets to the end of the field, then it'll shoot out the other end, like that. Something like that. Now, using the other version of that right-hand rule, if the velocity is in this direction, we put our fingers in the direction of velocity, and we curl our fingers toward the direction of the field, we get the force going up as well. So either version of the right-hand rule gives you the same result. Now, funny thing though, if we take instead of a proton, a neutron, right, with no charge, give it the same velocity, it's going to go into this field and it's going to pass right through it like nothing happened. Because it's not generating a field. Now, conversely, if we take the positive and instead make it an electron and shoot that electron into the field with a velocity v, what's going to happen is the electron will behave opposite what the right-hand rule says. So the right-hand rule tells you what a proton will do in that case. So in this case, if a proton is going to experience an upward force, the electron will simply experience a downward force and curve out like that. Okay, so there's two versions of the right-hand rule. Now, the last thing we want to look at today involves in this video involves right-hand rule number 2. And it's going to be the basis of our study of the motor for today. Now, we've talked a lot about solenoids, right? Which are long, successive loops of coiling wire. And we know that if you run a current through that it will form a magnetic field inside the solenoid. Now, right-hand rule number 2 tells us if we wrap our fingers in the direction that the current is physically moving, then like that. Our thumb points to the North Pole. So the North Pole is here and the South Pole is here. Now, if we further insert an iron core, a ferromagnetic core inside of this, we can get a field that's hundreds of times stronger. That has something to do with the permeability of free space being very low, but the permeability of a ferromagnetic material being pretty high. And so when we get this whole setup together like this with the coils of wire, the solenoid, and the ferromagnetic core, we call that an electromagnet. And an electromagnet has some features that are kind of interesting. And I want you to, if you think for a minute, you can see what the advantages to an electromagnet are. Let's first of all talk about, though, how we can vary the strength of the electromagnet. Now, what would you suppose would happen if we increase the amount of current going through here? And I know intuitively, you're going to say if we increase the current, we're going to increase the field, and you would be correct. Other thing we can do is if we increase the number of turns, we can also increase the field. That's a little ambiguous though, because the more turns we have, the longer the wire is and the more resistance is, which drops the current. So there's a trade-off there. Last thing is, the better the ferromagnetic material is, the better the field produced. So for example, iron would produce a better field than nickel or cobalt, and they would all produce a better field than something like aluminum. Now, that's the basic way to vary the strength, but I want you to think about the electromagnet compared to a permanent magnet, like a refrigerator magnet. The electromagnet has some pretty obvious advantages. First thing is, you can turn an electromagnet on and off, whereas the permanent magnet is always on. Second thing is, what would happen if we took our battery and we flipped it around so that this was positive and this was negative? Well, then by the right-hand rule, when we turn, we find that that becomes the North Pole, and that's the South Pole. In other words, the second advantage is we can flip the polarity almost instantly. Whereas if I wanted to flip the polarity of a permanent magnet, I would have to physically turn it and it would take some time. We can do this almost instantly. Now the third advantage is we can vary the strength. So all those things are advantages to this thing about the electromagnet. Now I wonder if you can think of any disadvantages to the electromagnet. I'll give you a second to think there. But the one obvious thing is, it requires a power source. Whereas these permanent magnets, which are just like the ones on your refrigerator, they do not require a power source. And in fact, if you stick one of them to your refrigerator, it will stay there virtually forever. Right? So these magnets, it's kind of strange, but as long as they keep their domain structure, it's like an endless free source of power. They never lose their magnetism. They never run out of magnetism. So anyway, this is going to set you up to understand how an electric motor works, which is our topic for today. So just remember these advantages and disadvantages, and remember how to sketch. All right, so I will post the second video in about 30-45 minutes. So good luck with the rest of your day.